Okay, welcome here, everybody. Today's talk is going to be about uncertainty in deep learning. We'll start by considering the setting of automated driving. So for the driver of a vehicle, either if it's a rule-based system or a learned system, we generally need some perceptive system for this. So consider here that you are the driver and you're seeing this view in front of you. So one of the things that you like is semantic segmentation of this image, which divides pixels into semantic regions. So for this image, the ground truth segmentation looks like this. We can see where there are pavements, where there is a tree, where there are signs, and where the area to drive on is. Now, pay attention to the streets going to the left. That is the bright purple area here. Because, as I told you, this is the ground truth. And your neural network that gives you your input for driving instead gives you this segmentation. You perhaps may have noticed on the street going to the left, it seems to have moved a bit from the ground truth. So if you're making a decision based on this input, chances are you'll be crashing into this sign or something. Now, imagine instead that your model can also do this. This is an estimation of the uncertainty of the prediction. And as you can see, the red areas to the left shows us that where the sidewalk is, that's also where this model is very uncertain. Right. So today's topic is uncertainty in deep learning. Now, deep learning is the sequential application of a number of transforms. Each transform looks something like this. We have an input vector x multiplied by a linear matrix w, and then we add some bias term to this and squash it through some activation function a. We train this using backpropagation and some optimizer. Normal or usual activation functions are the logistic function, the tanh function, the ReLU. And for a classification output, we usually have Softmax out. So we train this using the cross-entropy loss, and we sort of get a probabilistic interpretation of the outputs. It sums to 1, and it looks like a probability distribution. There can, however, be some issues with this, we will see in a minute. Okay, so imagine now that we are training a classifier to distinguish between cats and dogs. It's trained typically on these kinds of images. We see that cats have pointed ears and dogs look happy, I suppose. So what happens now if someone gives this model something else? A bird, for example, a yellow warbler. What should our model do? What do we want it to do? So some people at this point say that, well, we are training a probabilistic classifier, and it should be giving an uncertain response. And what is then an uncertain response? It could be that it gives half the probability mass to each of the two classes. But with a neural network or a softmax classifier, we always get a decision. We always get an output, a decision for either of these two classes, unless we train it to do something else. A softmax will give some sort of an arbitrary decision. This is also highlighted by other examples. For example, this Mauna Loa the CO2 concentrations data set. So standard deep learning model, and these are images by Gal, and I may have forgot to mention that sometimes during this presentation, but there are many images from Gal. So standard deep learning model gives you a point estimate, and many times it looks like it's confident about this point estimate. While a probabilistic model, as the one to the right here, it should give you some sort of a confidence indication. Now, what can the uncertainties be? So we classify uncertainties into two different classes, and aleatoric uncertainty is the noise that is inherent in the observations of the data. This means that the data could be spread out and have a lot of noise. It could be that we have faulty sensor readings. It could be that human annotators have been sloppy in the edges of the segmentations, for example. This error will generally not decrease with larger data and is also called the irreducible error or the Bayes error. Now, epistemic error is instead errors that's assigned to the model. So this could be due to parameter settings, or it could be due to the structure of it. It could also be due to having limited data, and that's what you can see in the image to the right, where you have not much training data. In those regions, you get high epistemic uncertainty because the model doesn't have much to train on. In regions where you have data, there may be aleatoric uncertainty instead. The epistemic uncertainty is in general reduced by increasing data. So going back to this self-driving car, we have the input and we have the ground truth on the top line here. Then we have the prediction, and in the middle we have an estimate of its aleatoric uncertainty. To the right, we have an estimate of its epistemic uncertainty, and this is the image that you saw in the previous slide. The epistemic uncertainty is something that you can estimate with some techniques for your predictions. The aleatoric uncertainty requires some other approaches, but it's also possible to do. And as you can see, the aleatoric uncertainty is higher in the edges between the different semantic classes, sort of the edge of the sidewalk or far away from the camera. Right, so I mentioned the Softmax outputs previously. So the cat-dog classifier, it doesn't know anything about the birds. And it will give an output. And it looks like it has a high confidence. It assigns a lot of its probability mass to one of the classes. And this is due to how the softmax function is defined. You can tweak this a bit with the temperature parameter, but the problem is still there. So on the bottom here is, again, an image by Gal, and where you have the input to the softmax to the left, and you have the output from the softmax to the right. And in general, it kind of prefers to put the output close to 0 or close to 1. Okay, so what are some of the remedies for this? Well, you can actually try to calibrate the softmax, and it works surprisingly well. So in this paper by Guo et al., they saw that neural networks from the 90s in general are better calibrated. That is, the outputs from the softmax are closer to a real probability distribution, or it's closer to the actual accuracy of its predictions. This is defined with using this expected calibration error. So if you look at the data points that has a certain confidence or a span of confidence, you'd like a certain fraction of those to be correct. So if the confidence is 0.8, you'd like the 0.8 fraction of those to be correct. And this, you can actually try to calibrate the output for this. So in the leftmost column in this image, we can see Lynette from 98 on the Cypher 100 dataset. And the confidences of the predictions are largely spread out. And the confidence here is the probability assigned to the largest class, that is the classifier decision. And now if you look to the right, and you see the ResNet from 2015, you instead see that the confidence is very high for most of the decisions, and the tail towards lower confidence, it's much thinner. So on the bottom right, you see this gap between the confidence and between the actual accuracy. So models have been developed, and they are much more accurate nowadays, but they are also becoming overly confident on the decisions. Now, the authors of this paper, they attribute this to the fact that we have larger models, and we're modeling using higher capacity models, and also the batch norm allows for larger models, and this, they show, leads to an overfitting of the negative log likelihood loss, even though it does not lead to an overfitting with regards to accuracy. So some of the solutions to this is to do histogram binning. Actually, all of these solutions are variants of the histogram binning. The binning means that you are taking the decisions, and you're taking the confidence of these decisions, and then you're binning them so that you have data points in certain intervals of the confidence. And then you're training an extra function that transforms from this softmax output, the actual softmax output, into this calibrated version of it. And it seems to do the job, which sort of indicates that even if the confidence outputs, they don't follow the true accuracy, we still have the correlation of it. Okay, what else can we do? So ensemble methods can be used to get an estimate of the uncertainty in a model. So for this example data here, we have a nonlinear regression problem, and training a 5 ensemble using just the mean squared error loss, it gives you some limited amount of an uncertainty score. So the idea of the uncertainty score from the ensemble is that each of the differently initialized with different random seeds, each model in the ensemble gives a slightly different prediction. And in areas where the models are unsure, these are more arbitrary and they vary more. So this difference in the random seed leads to different outputs, and it leads to a larger span in the outputs. Now, a single model trained with negative log likelihood, and that means that the model is outputting the mean and the variance of the Gaussian model, or Gaussian distribution, in this second column here. It gives some estimate of the uncertainty. But it seems to be rather limited. It doesn't go as large in the variation as we'd like. We'd like to see the blue ground truth line within the distribution. Okay, so this model also proposed an adversarial training of these that helped a little bit, and then together with ensembling and this negative log likelihood that gives you this mean and variance output, you get a much better estimate of the uncertainty. And this is actually an estimate of the epistemic uncertainty that we talked about before. Right. So now let's mention dropout. So dropout is the process of it was proposed as a regularization technique, and it works as a regularization technique. So independently with probability P, you set each input to 0 before each layer in a network. And in the original version, this is done during training. And then during inference, you set none of the inputs to 0, and it has been shown that the model generalizes very well from this. Now, you can also view this as an ensemble. So randomly, you're taking away parts of the neural net during training, and you're training subsets of the model. And in this way, you can see it as an exponential ensemble. Now, with Monte Carlo dropout, we run a network several times, also at test time. And we do this with different random seeds, which means that we're dropping different units in the network. And this essentially turns out that the network is then similar to the ensemble method in the previous slide. Now, the authors have also shown that this is the same as imposing a prior on the weights. Similarly, as L2 weight decay is equivalent to having a Gaussian prior. So in the paper, they try this method with the MC dropout, the Markov, the Monte Carlo dropout for active learning. And so they have a pool set, and they choose examples from this pool set based on the information as given by this Monte Carlo dropout network. So they view high uncertainty as high information, and then they're selecting training data points in that way. And it learns a bit quicker than doing the bold method. They also train deep reinforcement learning agents using Thomson sampling. So you're sampling data to optimize the cumulative reward, and you get increased data efficiency in the same way here. All right, so let's change focus a little bit here. Density mixtures networks is something proposed by Bishop in '94, I think. And this is actually something that were used in this ensemble that I mentioned previously, where they have the negative log likelihood loss. So in density mixtures, we're training a model to output a mixture of Gaussian outputs, and with enough of mixture components, you can approximate an arbitrary distribution in this way. Now you can train a regression model using the negative log likelihood loss, and you also get an estimate of uncertainty here. And this uncertainty will be the aleatoric uncertainty, as in contrast to the ensemble methods, which finds an epistemic uncertainty. So this is actually a work that John Martinsson and I, with co-authors, did a couple of years back. It was published this year. That's why it says 2020 here. So we trained a recurrent neural network to produce these densities. We trained this using the negative log likelihood, this was motivated by doing predictions on blood glucose concentration. So in the top line here, we see experiments on real data where we get the prediction and we get the variance estimation, which is the orange thick area around the the brown prediction line. The blue line is the ground truth. And to explore more of what we're learning with this mixture density networks approach, we trained this using synthetic square wave data, as you can see here on the bottom line. So in the leftmost picture, we have a deterministic wave, and the model, as expected, learns when to switch state and fits perfectly to this generated data. Now in the middle image, we vary the amplitude randomly, and the model does recover this square the square wave with an estimate of the variation of the stochastic amplitude. Similarly, in the rightmost picture, bottom right picture, we have the variability instead in the period length of the square wave, and as expected, the model learns when the state is deterministic, and then in the end of each period, the variance goes up, and that's much expected because we never know exactly when the switch is going to happen. The switch does happen within an interval here. Right. So a little bit of switching gears here. Introducing Bayesian machine learning. Now Bayesian machine learning, we encode and we incorporate prior belief. And we do this as a distribution of models or model parameters. And we're after posterior over the model parameters. And as you see in the Bayes rule in the bottom, this you have all seen many times, we have the posterior, which is the probability of the model given some new data. And this is expressed with the likelihood and the prior and the evidence term. Now, doing inference over the posterior means that we need to marginalize over latent parameters. And with large models, this is really expensive. Large models with parameters in continuous space, this marginalization means that we have to compute an expensive integral. And this is in the evidence term that we're doing this. So for simple models, we can use conjugate priors, and we can get closed form solutions. But this is in general not that simple. Approximate Bayesian methods include variational inference and Markov chain Monte Carlo sampling to make these estimations. Right. So for some comparison here, we have on the top equation here, we have the weights as estimated by maximum likelihood, the MLE here. And then we're looking for maximizing with regards to W. We're maximizing the log likelihood of the model. We can go one little step towards Bayesian modeling by doing the maximum a posteriori, where we look at the likelihood and also the prior of the model. And that can give you a maximum posteriori estimate of the weights for a model. Now, the true posterior, it includes the expectation or using the true posterior for making a prediction. It includes the expectation over the true posterior for this predictive probability. And this is equivalent to using an ensemble of an uncountably infinite number of models, which of course is expensive. So in comes variational inference. Okay, so the true posterior is intractable in general. To cope with this, we introduce this variational distribution Q, which is parameterized by theta. And then we want to minimize the Kullback-Leibler between Q and P with regards to theta. This gives us a predictive distribution that looks like this, where we're replacing this integral over the parameters which are called omega here. We're replacing those with this Q theta of y and x. And we need some tricks to train this, of course, train the Q. So minimizing this Kullback-Leibler divergence is equivalent to maximizing the evidence lower bound. And in this elbow, the evidence lower bound, we have the left term, which is to minimize maximizing the likelihood, and the second term, which is the KL between Q and P, which is the model to go close to the prior. Right. But we're talking about deep learning, right? So in comes Bayesian neural networks. Now, in a Bayesian neural network, we put a prior on each weight. That means that we're replacing each parameter in the network, and we can have thousands or even millions in a normal neural network today. We're replacing them with a random variable, which means that we now have a distribution over possible values. So in the variational approximations for this, it includes numerical integration, but we do this over the variational posterior, which can sometimes be easier than to do it on over the original posterior, the true posterior. So base by backprop is one way of doing this, and for this, the variational free energy is used. This is the elbow on the marginal likelihood. So these methods are proposed both to improve generalization, but also to give these estimates of uncertainty in a similar way as the ensembles do. And in fact, the authors Jorin Gal and Zubin Garmani et al. They showed that the Monte Carlo dropout is equivalent to having a real Bayesian formulation. So in the plots here, we see in the left plot, we see a network trained with base by backprop, and we have a regression of noisy data, and we see all the training data as the black X's here. And we see the prediction mean as the red line. And then we have quartiles, which are blue and purple regions here. So you can see in the leftmost picture that as you get farther away from the training data, the uncertainty increases, which is expected and wanted. In the standard neural network to the right, the model is trained with the same. It produces the Gaussian output. So you have the mean and the variance predicted by the neural network, and it's trained using the negative log likelihood. But the uncertainty estimates in this case aren't that convincing, as they don't show the property of getting larger as you go farther away from the training data. So there's been a number of publications on this topic since the seminal publication by McKay in '92. So some papers that could be suggested for reading is from Alex Graves in NeurIPS 2011, and also Blundell et al. In ICML 2015. Some notes on Bayesian methods, and these have been made by Zubin Garmani, who is a proponent of Bayesian methods. So advantages of Bayesian methods is that you have coherency, and you have some sort of a straightforward conceptual idea of the whole thing. You have a modular decomposition of the things from the Bayes rule, and you can get really useful predictions. And this is, of course, a major selling point here. Some of the criticism of Bayesian methods is that introducing the prior is subjective. And you introduce your own assumptions in the prior. Now, the prior can be designed, of course, by using expert knowledge, or it could be used, you could use data for finding it. But you need to get this from somewhere, and it may be a challenge to get it not to be subjective. The methods are computationally demanding, and you have the integrals to compute, even if the variation can sometimes replace the variational methods can sometimes replace the integration with optimization. Yet again, then the approximations also may weaken the coherence argument in the way that we're not training for the true posterior, but we're training a variational estimate of it. As I mentioned, the authors of the Monte Carlo Dropout paper present this as an approximate posterior, and this is equivalent to an approximation of deep Gaussian processes. Okay, so we are now in the slides regarding papers published in NeurIPS 2020, which is in very soon now. So one of the papers look at stationary activations for uncertainty calibration in deep learning, and they present this Matern activation function that train a network. This looks like a little bit of a peculiar activation function. You see the formula in the middle, but you also see the plot of the activation function to the right. And as you can see, it's not a monotonic function. In contrast to most activation functions that are used in neural networks today. Instead, it increases after 0 and then goes back to 0 later. But apparently, this gives improvements in the uncertainty estimates for a Monte Carlo dropout network. If you look at the images, the plots here, the gray background means that the model is is uncertain or have a low confidence. And the white areas is where the model is confident or have a low uncertainty. Now, if you look on the top right plot, these estimates, I would say, look fairly good in the way that you have bright white areas close to the points, and then you have darker areas closer to the decision boundaries and farther away from the points. Now, the top line here is for a Gaussian process. So that is a non-parametric method, or an infinitely wide neural network, if you like. On the bottom line, you have a finite neural network instead. So you have a finite width of neural network, and there I'm not sure that they convince me equally well. On the bottom right, you have the Matern 5/2 activation function. So this is what they are proposing. But I suppose that it may look a little bit better than the other columns. They have some really nice motivations for this, so it could definitely be worth a read. So another paper look at counterfactual autoencoders in causal effect inference failure detection. So in these plots, you have the top line where you have untreated patients. So the setting of counterfactual or causal effect inference models is often that you have a treatment or you have an untreatment or zero treatment for a patient, and you'd like to do some inference on these patients, and ultimately you'd like to see what happens if we change the treatment for a data point or for an individual in the data. So they train a network also with the Monte Carlo dropout to get some epistemic uncertainty and to detect the covariate shift in these networks. And I think this plot is for a toy data set where we have a one-dimensional input to demonstrate the different regions here. So top line is, I mentioned this, untreated patients, and middle line is treated individuals, and the bottom line is the uncertainty in the model. And if you see the colored regions along the x-axis on the bottom line, you see the pink regions, which are in distribution, where we have training data in both treated and untreated patients. And we have the regions with light blue where we have where we're missing data in one of the two, and then we have the regions where we are missing data from both cohorts. So we have an auto distribution setting. So those are the dark blue, and the model detects these with some success. So there are also experiments, obviously, on real data in the paper, and it looks really good. So some other papers that may be interesting to look into, but which are out of the scope today, also will be presented at NeurIPS 2020. So depth uncertainty networks, that's the image in the bottom here, where we get uncertainty estimates by having the depth of the network being a stochastic variable. We have another paper by Wenzel et al. Looking at hyperparameters and ensembles for robustness and uncertainty quantification, where ensembles vary not only on the parameters, but also on hyperparameters. Other papers that look interesting are deep subensembles for fast uncertainty estimation and image classification by Valdenegro, Toro, et al. And also beyond the mean field, structured deep Gaussian processes improve the predictive uncertainties. These are really descriptive titles. Simple and principled uncertainty estimation with deterministic deep learning via distance awareness. So these are some papers that could be worth looking into. I don't have time today to go through them. And as one last remark here, there are a couple of ways of getting started. So last year, Bayesian layers was presented, which is a module for neural network uncertainty, which ties into several different popular machine learning toolkits. EdwardLib is a comprehensive library for probabilistic modeling, and it can be found on edwardlib.org. So these are things that you could start looking into if you're curious on starting experimenting with these things. Right, so I'll just end with dropping the reference list on the screen, and I'll be happy to take some questions.